Hey everyone, here we go with 3.2. So we're going to get more into some probability with some advanced concepts like conditional probability and the multiplication rule. So to start it off, let's look at what conditional probability is. This will make no sense, but maybe more sense once we do an example. Um, it's the probability of an event occurring given that another event has already occurred and we have a notation for it. So when you see this notation, you read that as the probability of B given that A has happened. All right, so we're looking at probabilities where we know something has already occurred, which sometimes will change the probability of the next thing happening. That makes sense? Let's look at some cards and try to make sense of this. So on number one, it says the ace of spades has been removed from a standard 52 card deck. There's your condition, right? There's something that you know has happened in advance. And now a new card is randomly selected from the deck. What is the probability that that card is an ace, given that the ace of spades has been removed? In other words, if I go back up to my table here, let's maybe make it a little bit cleaner, erase all that out. I know that for one, the ace of spades, this card right here, has been removed. There we go, block that out. All right, it's gone. Now, notice there was 52 cards, now there's only 51 left. There were 4 aces, now there's only 3 left. Okay, so if I'm going to find the probability of the next card being an ace, it's going to be 3 possible cards out of a total of 51 total cards in the deck. All right, so I can go back up to my, or down, I guess, to my problem and write that. The way I would write that is probability that we select an ace, given that let's say ace of spades has been removed. So sometimes you can just write out the whole thing, right? Okay, and that we said was 3 out of 51. That reduces to 1 out of 17, I'm pretty sure. 3 goes into 51 17 times, okay? So there's one type of conditional probability. It will change the counts when you set up your fraction. Here's another kind when we get to things like two-way tables. So we have child's IQ versus we have the gene present or not, okay? Let's take a look. We're going to choose one random child from the study. What's the probability that the child has a high IQ? So if I look at these numbers, I want to set up a fraction here. I know we're choosing from a grand total of 102 children. And of those 102 children, how many of them have a high IQ? I can look at that total for the high IQ, 52. Right? And this one says, write your answer as a decimal, rounded to 3 decimal places. Where did my calculator go? I'm always losing that thing. Okay, 52 divided by 102. Gotta turn it on. Okay, 0.5. I guess we're gonna go with 510, right? If you're rounding correctly. Okay. How about that the child has the gene present? So again, there's still 102 of them. What's the total that have the gene present? Total is 72. All right, 72 divided by 102 is 0.706. All right, those are some standard probability questions. Now we get into the conditional probability. A key word for conditional is given that. So if you see that term, given that, the condition is what follows it, given that the child has the gene present. We already know the child has the gene present. Therefore, that's going to change your denominator. We're not choosing from everyone. We're choosing only from those that have the gene present. So whatever follows the given that statement will define your denominator. Go and find the total number of students or children that have the gene present, which is that 72. Okay, and then decide, okay, of those 72, how many of them have a high IQ? So now I'm just looking at this column here, right? There are 72 total, 33 of them have a high IQ. There would be my answer. 33 divided by 72, 0.458. And we've got it. Okay, so let's try another one of those. Child has the gene present, given that the child has a high IQ. Start there, right? Given that the child has a high IQ. Let's go back up top. Let's get rid of all this. It's kind of a mess. All right, given that the child has a high IQ, boom, there's 52 total children that have a high IQ. That's the denominator. Of those, how many have the gene present? There it is, 33. Stay within that one row or that one column for these. Okay, and then just do the calculation and you're good to go. I'm getting 0.635. Okay, fun times. Next page, we've got some more terminology. Independent events. Two events are independent if one does not affect the probability of the other. Okay, so like, flipping a coin and rolling a die, they're not going to affect each other's probabilities, right? That's independent. Okay, when two events are independent, the condition of one happening doesn't matter. Probability of B given that A has occurred is the same as probability of B, because who cares what happened with A? It's not going to affect the probability of B. To practice this a little bit, here's some examples. Decide, number 3, whether the events are independent or dependent. So event A is you select an ace from a deck and you don't replace it. Then you select a queen from the deck in event A. Notice that because you did not replace that card, that's going to affect the probability of event B, right? So if the probability gets affected, it is dependent. What happens here in event A is going to change the probability of event B. If we put the card back, it would be independent. So without replacement is a pretty good indicator of dependent. With replacement would be independent. Number 4, event A is tossing a coin, and event B is rolling a die. Those aren't going to have any effect on one another, so that's independent. Now, why is all this important? It has to do with the multiplication rule down here. So there's a standard formula for the multiplication rule. It's the probability that two events A and B occur in sequence. So and is a key word for these. The probability of A and B occurring is multiplication. The probability of A multiplied by the probability of B, given that A has occurred. Okay. Now, if the events are independent, that given that part doesn't matter. So you have a simplified formula for independent events. It's just the probability of A times the probability of B. Just multiply the probabilities together. Okay, so let's take a look at some examples. We'll see some independent and some dependent examples going forward, and we'll try to get used to that. Okay, let's see. We've got 2 cards are selected in sequence from a standard deck. The first card is not replaced. That's the key. You don't put that card back. So that's going to be dependent events. Find the probability that both cards are aces. The first card is an ace, and the second card is also an ace. So probability of both aces. I know I'm going to do here is multiply 2 probabilities together, right? And take it one selection at a time. So the first fraction is, what's the probability that that first card is an ace? If it helps, go back up to your thing here. Erase that blob. All right, remember there are 4 aces in the deck, and there's a total of 52 cards in the deck. So that's 4 out of 52. Okay, back down to my problem. Where'd it go? There it is. My first probability, 4 out of 52. That's the probability that the first card selected is an ace. For the second fraction, we're going to assume that the first card was an ace. We're going to assume that success and not replace it. So we're going to take an ace out of the deck. So that second fraction, the numbers are going to change. What's the probability now of getting an ace if one of the aces has been removed? So now there's only 51 cards total, and only 3 of them are aces. Okay, that's the conditional part of this multiplication process. Okay, now it's just math, right? We got to multiply these together. Well, those both reduce. 4 over 52 is the same as 1 over 13, right? 3 over 51 reduces to 1 over 17. Okay, so I'm just doing 13 times 17, just 221. This is 1 out of 221. Okay. All right, we're getting there. We're doing it. All right. Let's try one more problem for this video. The probability of a particular knee surgery being successful, 85%. Anytime you're dealing with probabilities and you have to do some calculations, convert those to decimals. 85% is 0.85. Okay. And then the knee surgery is performed on 3 different people. A, find the probability that all 3 surgeries were successful. So, first surgery, the probability of being successful is 0.85. I'm given that. What's the probability of the next surgery being successful? Well, these are independent surgeries, right? So what happens on one surgery is not going to affect the outcome of another surgery. So that's going to be 0.85. And then the third surgery is still 0.85. Multiplying all of those together, it's the multiplication rule, all 3 successful surgeries, first and second and third. This is the same as doing 0.85 to the third power if you want to do a little shortcut on your calculator, doing exponents. And if we round this off, it's about 0.614. Okay. The next one, find the probability that none of the surgeries were successful. Okay, so if you have an 85% of success, then you have a 15% of failure, right? Because 1 minus 85 is 15. So for this one, I'm just doing 0.15 multiplied by itself 3 times, or 0.15 to the third power. 0.15 raised to the third power is 0.003. Okay, that's the probability that none of them were successful. And then the last one here, we've got the probability that at least one, ooh, there's that phrase again, at least one. Probability of at least one. Remember before that this was a complement to something? It was the complement to none. So a good way to do this is the probability of at least one is equal to the probability of equals 1 minus the probability of no successes. All right. Think of this as a little formula. I would use this a lot. Anytime you see that at least one in these questions, do 1 minus the probability of none. In other words, you're finding here, right? You're finding the opposite of really what you want and then just subtracting it from 1 to get your answer. Now we've already figured out the probability of none. That's B, right? Probability that no successes was that 0.003. So that simplified this. I'm just doing 1 minus 0.003, 0.997, and I'm good to go. Okay, so anytime it's at least 1 minus, you should be good. Give some of those in section 3.2 a try. We got another example we'll do in the next video. Otherwise, hope all is well. Talk to you soon.